السلام عليكم. نحكي بعد إذا في أي شيء. Lecture 13, we are still speaking about soil-water relationships or soil permeability, as you know. Let me just remind you of last thing we took. Okay? We want to discuss, to understand how water flows in soil, right? So water flow in soil. This is our subject. We said that by doing the experimental tests, or by doing the laboratory tests, or by doing the field test, or by using even empirical methods, we always have water flow in one direction, which is not the real thing. Okay? In reality, water may flow in several directions, not in one direction. Okay? So this is a limitation. We cannot just use what we studied in the laboratory or in the field to do it when we deal with soil in general, okay? Because we assume that water will flow in one direction, while in fact it flows in several directions. That's one thing. The other thing that is that water flow is not uniform. It's not uniform, okay? It may differ from place to place. So because of that, we have to understand the flow of water in soil by studying the case in the field. Okay? Doing this, we have to have this case. Okay? We have water flow. Water flow here. This is water. Okay? This is water. Water will flow from this side to this side. Okay? Now, if we put sheet pile, if we put any shelter, anything to prevent water from flow, we call it sheet pile, dam, whatever, okay? So water will not flow through this structure because it's impervious. It means no permeability. It means water doesn't flow through, okay? Of course, water cannot jump, okay? So the only way is for water is to go through the soil, okay? This is rock. This is rock. So we have rock, we have soil, and we have water. Of course, water will not be here unless it is already there below, right? Water will not reach that level unless everything below it is saturated. You should understand this, right? Water, when water is at this level, then everything below is saturated. So water is filling this area, okay? So it will go through this side and come here. That's why we have some water in front of the bridge, in front of the dams or whatever structures, okay? Now, what I want to know is to understand how water will go through this soil and what is the behavior. To do this, I picked an element, I called it A, an infinite element, okay? Just one point here, very infinite element, okay? Now, I'd like to study how water will flow through this element, okay? To do so, I enlarged that element to be a big cubic, as you see, okay? And of course, I gave the direction. This is X, right? And this is Y, and this is Z, right? Okay? So I have an infinite element. Infinite element means this distance is dx, right? From here to here. This distance is dz. And this distance is dy, okay? Because it's a small element. dx, dy, dz. It's a cubic, okay? Very small. dx, dy, dz. Now, I will understand that water will come from this side and will go from this side to go up. It's coming from here, so it will pass through these faces, okay? And some water will come from beneath and it will go like this. And some water will go from this side to that side, or maybe the opposite, from the side to this side. I mean that water will come from this side here, so I have some water like this, and maybe this way or that way. This is the same thing, you see? But I enlarged the picture, okay? I enlarged the picture. We go back here. Water will go in this directions as I saw, as I draw, okay? Now, I understand something. That is, flow in should be equal to flow out, right? Flow in should be equal to flow out. And of course, I represent flow. Remember this term, flow rate. Flow, we call it Q, right? Remember that? Okay? Q. So, I can say, instead of saying flow in equals to flow out, I can say also Qn equals to Q out, right? Qn equals to Q out. Flow rate inside equals to flow rate outside. Flow amount inside equals to flow amount outside, right? Okay. But I know that flow rate is velocity multiplied by cross-sectional area, right? We took this, remember, these first equations we took, right? Q equals to V multiplied by A, right? If anything is wrong, or if you have any questions, you just ask me immediately. Don't delay that, okay? So, Q equals to V multiplied by A. Now I will substitute this equation. I will use this to put it here in and out. But you see in our cubic, remember the cubic we draw, okay? This cubic. To make it easy for us, instead of dealing with the cubic with 6 faces, right? Let us make our problem 2-dimensional instead of 3 dimensions. Okay? Instead of 3-dimensional, let us make it 2-dimensional. That will make it easier for us to solve. Okay? So instead of having a cube like this, I will have just this drawing, okay? And let me say that this is dy and this is dx, okay? So where is dz? I just eliminated it, right? Because I'm dealing with 2 dimensionals, dx and dy, okay? Now in this case, I will have water in, water out, right? Water in, water out, right? Which means that I have 2 directions only, direction x and direction y, okay? Z is already, I don't have it. So now we go back to this equation, and let's see. Q in should be equal to Q out, right? Let us see what do we have in Q in. In Q in, I have this one, Q in the x direction, right? And I have Q in the y direction, right? These are the Q in, right? So let us put it in this way. Q in, it means that the flow inside, okay? Now, I have it in 2 directions. In the x direction, this is the x direction, okay? What do I have? I have Qx. I will call it Qx, okay? Qx multiplied by A. A is cross-sectional area, right? The cross-sectional area that will be subjected to this is, what is this distance? dy. And what is the distance in the depth? dz. So I multiplied it by dy dz. That's right? Okay. So Qx equals to velocity in the direction x, multiplied by the cross-sectional area, which is dy by dz, right? The same way in the y direction, Qy will be equal to velocity in the y direction multiplied by dx, and the depth is dz, right? Are you following? Okay. So what I did is I calculated the Qn. Qn, they are in two directions. If I put the third direction in z direction, it will be Qz equals to Vz multiplied by dx dy, right? Okay, but I have two directions only, so two-dimensional. So in the x direction, I will have Qx equals to Vx by dy dz. Qy in the y direction, it equals to velocity in the y directions by dy dz. Dx dz, okay? Now, sorry. Okay. Now we will go to the Q out. Okay, Q out. Q out, I'll put them in red. The Qx will give me Qx out, right? Qx out. This is Qx in. It will go, and then it will be Qx out, right? And this will be Qy out, right? I have two inside, then there I will have two outside. Now, this out, here are they, Q out, Q out. In the x direction, I will have Qx. What it will be? Qx equals to velocity at the side x plus, this is written, this should not be here. This should be here. Okay? I will write it here in a way that you can see it. Qx equals Vx plus dVx by dx along dx. Remember this? We said it last time, right? This is the partial, right? The partial. dVx by dx along dx, all together multiplied by the same dy dz, right? The same dy dz. Okay? Now, the same thing for the y direction. Qy equals Qy out equals Vy plus partial of dVy by dy along dy multiplied by dx dz. The A. Okay? So what do I have now? I have Qx inside, Qx outside. Okay? Qy inside, Qy outside. Okay? Right? But I know that Qin equals to Q out. So I can say that this plus this equals to this plus this, right? Qin equals to Q out. What do I have in? Qx in plus Q out in equals to Qx out plus Q out out, right? Qy out. Okay. Q in equals to Q out, as you see. Or Q in minus Q out equals to 0. I can put it in this way, right? Q in minus Q out, Q in minus Q out equals to 0, because Q in equals to Q. So I have to substitute only the equations that I just wrote. What are these equations? The in equation is Vx multiplied by dx dy, dy dz, right? Plus Vy multiplied by dx dz equals to, or minus, it will be equal to 0. Let me say equals to Vx plus dVx by dx along dx multiplied by dy dz, right? Plus Vy plus dVy by dy along dy multiplied by dx dz. I just substitute the in equals to the out, right? The in equals to the out. Or I can put it this way. Minus this one equal 0. Okay? The in minus the out equals 0. So Vx multiplied by dy dz plus Vy multiplied by dx dz minus Vx plus the partial multiplied by dy dz plus dy plus the partial multiplied by dx dz equals to 0. You wrote that. Okay? Now concentrate with me. If this equation equals to 0, let us see where do we have the 0. Okay? Now, Vx, can it be 0? Velocity in the x direction, can it be 0? No. Of course, if we don't have velocity, then we don't have water, so we don't have a problem to speak about. Okay? So Vx and Vy, right? It cannot be 0. It cannot be 0. Right? They cannot be 0. Otherwise, we don't have flow of water and we don't have a problem that we are looking for. Okay? Vx, Vy, Vz cannot be 0. Okay. Let us ask another question. Dy. What is dy? The small distance in the y direction. Dz, dx, dy, dz. Can they be 0? Then we don't have an element, right? We don't have an element. So this cannot be 0. 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 But they should be, the equation should be 0. Then from where the 0 will come? From the partial. I put it this way. The dvx by dx plus the dvy by dy, this is equals to 0. So the partial is 0. This is equation 1. We can put it, this is equation 1. So this should be 0. Okay? So the partial dvx by dx plus the partial dvy by dy equals to 0. Because the velocity cannot be 0, the distances cannot be 0, so the partial is 0. Okay? dvx by dx plus dvy by dy equals to 0. This is equation 1. Okay? This is very important. Now let us go and remember, I told you, you have to remember his name, right? His name is very important. Darcy. What is Darcy's law? V equals Ki. You should remember it. You should not mistake it. Okay? V equals Ki. We will use Darcy's law, which says that V equals to coefficient of permeability multiplied by hydraulic gradient I. Okay? We know this equation. V equals Ki. I will substitute this in the derivations that I took. I will say that velocity in the x direction then equals k in the x direction multiplied by I in the x direction. Right? And v in the y directions equals to k in the y direction multiplied by I in the y direction. Right? Which is here k in the x directions. What is I in the x direction? I is hydraulic gradient, right? Remember? I equals delta H over L, right? Which means that the difference in level divided by L, right? Remember? Delta H divided by L, right? But when I am talking about very small element, remember? Then can I put it in this way? Partial of H elevation by partial of the distance x. Okay? So it's kx dh over dx. Okay? This represents I. Because it's very small element, so instead of I, dh, delta H, change in level, by L, then I will put it change of height, delta, partial, dh by dx, okay? And the same thing, dh by dy, okay? This is equation 2. Now I have two big equations. The first one is that the partial equals to 0, right? Right? dx over d, what we said, dv over dx plus dv over dy equals to 0. By the way, if we have it in 3 dimensions, then plus dz, dv by dz equals to 0, right? And here, I used Darcy's law to reach that Vx equals to Kx partial of dH over dx, okay? This is equation 2. Now, I will put equation 1 in equation 2, okay? I will use equation 1 and equation 2, but knowing this thing, in very small element, can I say that Kx equals to Ky equals to Kz? Because it's very small element, there is no change. So Kx, Ky, Kz, they are equal, and let me call them K, just K. Okay? So use 1 and 2, knowing that Kx equals to Ky equals to K. I will use just K, not Kx, Ky, because they are the same. Okay? And if I substitute all together, I will end up with this equation. Okay? If I put them together, I will end up with this equation. Kx, of course it will be K, right? Kx, partial square of h divided by dx square plus Ky, d square h by dy square equals to 0. This is the result of 1 and 2. Okay? And now, of course, I can take Kx and Ky out to be K multiplied by d square h by dx square plus d square h by dy square. This is equals to 0. Okay? Now another question. K cannot be 0, right? K cannot be 0 because this is coefficient of permeability. K cannot be 0. K, no way to be 0. Then, what will be the 0? The partial. Then, d square h by dx square plus d square h by dy square plus d square h by dz square if it is 3 dimensions. This will be equal to 0. And this is what we call Laplace equation of continuity. You should be familiar with this. Laplace equation of continuity. You took it in math, you took it in physics, you took it in fluid. Right? Differential equations. Laplace is famous for his differential equations, right? That's why you don't like him. Laplace. From where he is? From where he was? Germany. No way, sir. It shouldn't be. From the name, Laplace. French. Low. When it comes always, it's like al-ta'rif in Arabic. That. Or even it may be also like the nisbah. Nabil-C. Okay, Laplace. Laplace equation of continuity. Laplace is very famous, by the way. Laplace has discoveries, mathematical discoveries, which enabled us to know that we have Uranus, Neptune, and Pluto. He discovered them mathematically and died before seeing them. But using his mathematics, then after 4 years of his death, we found Uranus. According to his math understanding and calculations. Laplace. He's very famous in mathematics, in astronomy. in astronomy? French Laplace. Okay. Laplace equation of continuity. It's an easy equation, you see. It's just d square h by dx square plus d square h by dy square plus d square h by dz square if we have the three dimensions. It's easy, equals to 0. It is easy. Writing it is very easy, but solving it is very complicated. Solving these equations, guys, is very complicated. It is very complicated. So, there is a suggestion to use graphical solution. There is a suggestion to use graphical solution. Graphical, drawing. Solution by drawings. Okay? Or what we call it, flow net. flow net. flow net. شبكة الجريان. So we will be talking about flow net, how to construct it, how to build it, how to use it, and how to benefit from it. Okay? This will take 2 weeks maybe to finish it. By the way, we are running very quickly, right? Okay. Flow net. Flow net. If we want to build a net, net for catching fish, okay? Of course, we will use ropes, right? Okay? No, now, do you think how many directions we will put the ropes in? Minimum. Minimum 2. If we are making sujadat salah, carpet, okay, and we use ropes, okay, or whatever, okay, at least we should have how many directions? We cannot make a carpet just by using ropes in one direction, right? It will not work. We can do it by having 4, 5, 6, 7 many directions, right? Right. Like for example, I can put like this, and then I'll put like this, and then I will put like this, and then I may add even like this. Whatever I can use to make a net, I can use many directions to put lines in it, okay? But the minimum 2 directions, right? 2 directions. We can make carpet out of 2 directions. One direction like this, and the other direction like this. For example. So it can be in 2 directions minimum. Okay? So to build a net, we need at least 2 directions to have ropes on these directions, right? Okay. But we need to answer 3 questions. 3 questions. The first question is, let me draw a net like this. Okay? This is one. This is a net, okay, in 2 directions, right? But I have to answer 3 questions. The first question is, what is the distance between a rope and another? Okay? What is the distance? Because if it is like this, it's not like this distance, right? So the distance differs, right? So I have to choose what is the distance between. You remember the sieve analysis, the sieves that you used it for sieve analysis test, right? So the distance is fixed, right? It should be fixed, right? It's constant. It should be fixed. Okay, this is one thing. Now, see this. This is 2 directions, right? And this is 2 directions. And this is 2 directions. right? And even this is two directions, right? So the other question is, what form of shape I will construct by using these lines, okay? So first one, how far, what is the distance between the two lines, okay? The other thing, what shape we will form, okay? These are very important. The third thing, when you go to shopping and you want to buy carpet, although we are getting to summer, right? But maybe it's cheaper. If we go to to buy a carpet, the first question he will ask you, the salesman, what size, right? What size your carpet? What size you want? Because if you want, for example, 2 by 3, it's not like 4 by 5, right? You cannot say, oh, 4 by 5, it's 200 shekels, for example, 200 dinars, okay? And the 2 by 3 is 180. Let me take the 3 by 5. No, because you have a room smaller, okay? So it's not good to have 4 by 5 when you have a room 2 by 3, right? So the first question he will ask you is, what size you want? Because if you like that carpet, but he told you this is the minimum 4 by 5, you will not look at it because you don't have this size of room, right? Right? So this is the third question. The first question is, what is the distance between the lines? The second question is, what shape we will form? The third question is, what's the boundary conditions? I may say that I want a carpet 2 by 3, or let me put it in this way. I can say that the distance between Nablus and Tulkarm is 27 kilometers, right? I can say this. Or I can say that Nablus is located at, and I'll give you two numbers, okay? The x and y directions. Remember in geography you took this, okay? Okay? And Tulkarm is line so and so, vertical, horizontal, etc. I can give you the location, okay? Ihdathiyat, okay, the location. And I can from this find that Tulkarm is away from Nablus by 27 kilometers, right? So I can put it different ways. Either I can tell you that I want a carpet 1 meter by 2 meters, or I can tell you, okay, this point is 0, 0, this point is 0, 12, this point is 12, 0, this point is 12, 12, for example, right? You took this in survey, you took it also in drawings, engineering drawings. These are three important questions I have to answer, okay? What is the distance between the lines? What is the shape that I will form? And the boundary conditions or the size of the field I will deal with, okay? Now, from the beginning, let us say this. When we will construct a flow net, I will have two lines, okay? I will have two lines. These lines are the following, okay? Flow net. Two lines. First line, stream, but nobody uses this word anymore. Little, okay? You will not find this word is used very much, okay? You will find instead of it flow. Flow line, okay? So I will have flow line. Flow line. In some books, streamline. Streamline or flow line, the same, okay? So either flow line or streamline. We will use flow line, okay? Flow line. And it should be, you put line under should. It should be represented by a solid line, okay? It should be represented by a solid line. Flow line, okay? Flow line. It should be represented by a solid line. What is flow line? It is the path of a drop of water from one place to one place, okay? If I pour some water here, the water will go down, okay? So the path of the water, this is a flow line, okay? Okay? Flow line is the path of the water, okay? Drops of water. How many drops of water we have in a tank?
Infinity.
There is nothing called infinity, okay? Too much. Let us say too much. Okay? Let us say too much. Okay. The other line is equipotential line. Equipotential lines means the line of equal potentiality. Okay? Equipotential line, it means that in this line, at every point of that line, potentiality is equal. That's why we call it equipotential line, equal potentiality line. And it should, it's not up to you. You don't have democracy here, okay? You have dictatorship. It should be represented by this type of line, okay? That's solid line. This one is not solid. Okay? So we have lines in two directions. One of them flow line, which means the path of the water, and the other one is equipotential line, which means that at this line, at every point of this line, potentiality is equal. Potentiality is the same. Potentiality of all points of that line is the same. It means that if this is an equipotential line, water will be above that line to the same height, right? Because the potentiality of this point and that point and every point on this line will rise the water to the same height because it has the same potentiality, okay? So water will be above this line at the same level, okay? At the same height, at the same level, okay? So, the first thing, we will have two lines. One is flow line, which is paths of all drops of water, and it will be represented by a solid line. And the other thing is equipotential line, the line of equal potentiality, which will be represented by this kind of line. Okay? Let us draw this drawing, and you don't need to draw it. Let me draw it just now, and then we will speak about it later. Okay? Suppose I have a dam like this. Okay? And of course, this dam is built in the earth. Okay? And this earth will, suppose I have here, what does this mean? Rock. Okay? So this is no water is here. Now, if we have the river here, okay, this is the height of the river, water will go beneath and it will come from here. Okay? Suppose this is H2 and this is H1. Now, what will happen? Water will go through the soil and comes here, right? Water elevation is H1, water elevation is H2, and this is the soil elevation H3. And water will go from here to there. Of course, water will not be able to go through the dam or jump above the dam, right? How we will draw a flow net here in the soil? How we will draw a flow net in the soil? Okay, you don't need to draw it now, because next time I will draw it to you and I will explain how we deal with it.